Refraction, calculating angles and refractive indices. So far we learned that refraction can occur when a ray of light travels from one medium into another. In the second part, we will learn how to calculate an unknown refractive index or an unknown angle. Should you be one of the many students who find rearranging formulae challenging, then have a look at the topic Essential Mathematical Skills to build your understanding in this area. The formula used here is Snell's law. Snell's law says that the ratio of the refractive indices is equal to the inverse ratio of the sines of the angles. In other words, I have a cross relationship here. If n1, the refractive index of material 1, is at the top of my fraction, then sine theta 1 needs to be at the bottom of the fraction. Let's look at an example for calculating an unknown refractive index. In this simple experiment, I measured the angle in perspex to be 40 degrees and the angle in air to be 68 degrees. Given that the refractive index of air is 1, I can now find the refractive index of perspex. We have n air equals 1, theta air equals 68 degrees, and theta perspex equals 40 degrees. So I can write n perspex over n air equals sine theta, note I put air at the top, to obtain the cross relationship, and I use sine theta perspex as the denominator of the fraction. I am now resolving for n perspex, as that is what we are looking for. So as n air is in the denominator, I multiply both sides by n air. So I get n perspex equals sine theta air over sine theta perspex times n air. Replacing the symbols with values, I get n perspex equals sine 68 degrees for air over sine 40 degrees for perspex, multiplied by 1 for the refractive index of air. Putting the numbers into my calculator, I now obtain approximately 1.44 for the refractive index of perspex. This is reasonably close to the theoretical value of 1.49. Let's have a look at how to calculate an angle using Snell's law. Let's take a ray of light shining into water. At the top is air with n equals 1, and at the bottom is water with n equals 1.33. Let's say that the ray of light will enter from the right at an angle of incidence of 80 degrees. The ray is refracted towards the normal, as the water has the higher refractive index. Using Snell's law, I will now calculate the angle of refraction, which here is the angle in water. As I am interested in an angle, I am writing the angles on the left. Note that I have the cross relationship again. Multiplying both sides by sine theta air gives me sine theta w equals n air over nw times sine theta air. To get theta w from sine theta w, I take the inverse of the sine. So theta w equals sine inverse of n air over nw times sine theta air. Putting in the values, I get sine inverse of 1 over 1.33 times sine 80 degrees, which is approximately 47.8 degrees. Using my protractor, I could now draw my ray diagram with the exact angles. What practical relevance does this have? Say you would see a fish in water in this position. Due to refraction, the fish appears in a different place to where it actually is. Using Snell's law, you would be able to calculate at which angle of refraction the fish would actually be. Another example is the design of car headlights. Various models differ significantly, but all of them use refraction. This type uses what looks like little blocks of glass. What you want from the headlights is that the rays shine right ahead of you, so you can see the road clearly. What you don't want is the illumination of the side of the road. Let's have a look at a cross-section of a headlight. Here is my light bulb. The light is radiated out in all directions. These rays, highlighted in green, are useful for shining to the front. The rest is wasted. Adding a curved mirror at the back allows the light to be reflected towards the front and thereby become useful. However, let's look at where refraction is applied. These rays that simply point slightly in the wrong direction can be useful if redirected. At the front of your headlight, you have the glass window. I'm only drawing the first air glass boundary. If I draw my normal, I can see that the light must be refracted towards the normal. Before drawing my second boundary, I can now draw the ray of light as I want it to leave the glass. Now the designer of the lights would have used Snell's law to calculate the angle at which the surface of this glass block needs to be inclined. I'm sketching the surface here, also adding the normal. As my ray enters air, it is refracted away from the normal. For a neighboring ray of light, my angles are slightly different, and I need a different inclination of the glass-air boundary. So overall, I end up with different blocks of glass with different surface angles. That explains why you see the glass blocks. Let me summarize. In a nutshell, Snell's law shows the mathematical relationship between the ratio of the refractive indices of the two materials and the ratio of the sines of the angles. This relationship is inverse, meaning a cross relationship. So if the refractive index n is the numerator of the fraction or ratio, then the associated sine θ1 must be in the denominator, and vice versa. In simple terms, Snell's law allows me to calculate either a missing angle or an unknown refractive index.